We are taking this from the Eastern Cape, September 2018. Different frequencies of light are shown onto a sodium metal plate, and the maximum kinetic energy of the ejected electrons is determined each time. A graph of maximum kinetic energy versus frequency for the metal is shown below. 10.1. Define the term work function of a metal. So this is the minimum energy that is required in order to eject electrons from a metal surface. 10.2. Write down the value of the work function of sodium metal. Okay, so here we have the graph of EK max versus the frequency. If we take this formula and rearrange it, we'll have EK max E minus WO, but E is given as H multiplied by the frequency WO. So this gives you the equation of a straight line. Y is equals to mx plus c, where y is the EK max, the gradient is Planck's constant, and then the x, on the x-axis you have the frequency, and then the y-intercept will be the work function. So wherever the graph cuts the y-intercept, that is where your work function will be. So in this instance, the work function should be equals to 3.51 multiplied by 10 to the exponent of negative 19 joules, because the units there are times 10 to the exponent of negative 19. 10.3. The same light photons are incident on the zinc metal, which means they don't change the light that is being used. So the frequency remains the same, the energy remains the same. How will the gradient of the graph for zinc metal compare to the gradient of the graph for sodium? Write only less than, greater than, or equals to, and give a reason for your answer. So we've already established that the gradient is Planck's constant, and the constant of this constant right here, it won't change because it is Planck's constant. That value will always be 6.63. It doesn't matter whether you change anything else or you don't change anything, but this value of the constant will not change. So the gradient should be equals to then 10.4. Calculate the frequency FO indicated on the graph. We already know that the wave function, the work function is equals to 3.51. So in order to find FO, we just substitute the work function, and this is Planck's constant. So I'm getting 5.29 times 10 to the exponent of 40 hertz. This is 10.4.1. the wavelength of the incident photon that correspond to the frequency f indicated on the graph. So when we look at f there, we have a graph that looks like this, and then so f there corresponds to an EK max of 3.83. So the EK max should be equals to 3.83 times 10 to exponent of negative 19 joules. So we are looking for the wavelength. E can be given as HF, or it can be given as HC all over lambda. So we are looking for lambda. So we'll use this part right here. So this should be HC over lambda. The work function we already have. And this is EK max. The work function is 3.51. And the EK max is 3.83 times 10 negative 19. So this side I'm getting 7.34 times 10 negative 19. And then 1.989 times 10 to the point of negative 25 all over lambda. Getting 2.71 times 10 negative 7 meters.